Prism. What's the meaning of angular dispersion and dispersive power? Here, this is a prism, and this is a ray, incident ray, that fall on its refracting surface. And if I draw a normal, this ray will bend in towards the normal. Different color is having a different deviation. Actually, it has to go in this direction. This is a red color, this is violet, and this is a yellow. So, angle of deviation for red is lesser, for violet is more, and then this is angle of deviation for yellow. If I talk about this thing, now angle of deviation is mu minus 1 into A. This is called angle of deviation. This is called angle of deviation. And that deviation for violet color is this one. And deviation for, if we talk about angle of deviation for violet color is this one, and angle of deviation for that's mu v minus 1 into A, and mu r is equal to mu this delta r is equal to mu r minus 1 into A. So these are the deviations. So refractive index, if this is number 1, this is number 2, I subtract number 2 from 1. So delta V minus delta R is mu V minus 1 into A minus mu R minus 1 into A. So it will be mu V into A minus A, mu R into A plus A. So minus plus cancel out. So mu V minus mu R into A is equal to delta V minus delta R. This is called angular dispersion. And angular dispersion for violet, this is the difference. This is called angular dispersion for violet and red components. In this case, clearly, angular dispersion produced by the prism depend upon two factors. Number 1 is this, nature of the prism. Number 2 is this, angle of prism. So, angular dispersion is depending upon the two factors. Angular dispersion is defined as rate of change of deviation with respect to wavelength. It is defined as rate of change of deviation with respect to wavelength. This is also called angular dispersion. Angular dispersion is called rate of change of deviation with respect to wavelength. And deviation we call mu minus 1 into A. This is called deviation, or you can write down it as a mu into A minus A is equal to angle of deviation. But we know that this was delta R V minus delta R is mu V minus mu R into A. This we can take delta D delta, and that's we can take means d mu into A. D angle of deviation upon d mu is equal to A. You can write down that's a small deviation of an angle upon small refractive index is equal to this value. But according to Cauchy's formula, mu is equal to A plus B upon lambda square. If I differentiate it with respect to wavelength, then it becomes equal to that's minus lambda square into B with respect to d lambda. So 2 power comes on another side, upper side. So this is this one. So 2 power multiplied in the upper side. So lambda power minus 2 minus 1 into b. It becomes minus 2 into lambda power minus 3 into b. So it is minus 2 into b upon lambda power 3. And we know that's angle of deviation, that d mu by, we can write down it as if that d mu by d lambda is equal to minus 2b upon lambda cube. So d mu into d delta upon d delta into d lambda, that's equal to minus 2b upon lambda cube. So this value, if we denote this value d delta upon d mu, what I did in this case, I multiplied this equation with, because earlier it was, if I consider in this case, this was the case, I am having this d delta upon d mu. What I do in here, I multiply it by, that's because in this case this was the value d mu by d lambda. So d delta by d lambda we have satisfied. What should I do? Here it was d delta by d lambda. And what should I do? I multiplied by d mu and divided by d mu. When I multiplied by d mu and divided by d mu, the value becomes equal to, so d delta upon d mu into d mu upon d lambda. So this value was equal to A. We have proven. So this was A. D mu by d lambda is equal to minus 2b upon lambda cube. So this is the value. So this comes to be this d delta by d lambda. So this is called as angular dispersion. So angular dispersion is inversely proportional to cube of wavelength. So we have defined it is inversely proportional to cube of wavelength. Secondly, we denote angular dispersion is inversely proportional to the cube of wavelength of A. As a result, prism spectrum is spread more for a violet as compared to red. So it will spread more for a violet as compared to red. Secondly, in this case, we are having this was delta V in minus delta R, that was mu V minus mu R into A, and this was delta upon mu minus 1 into A. If I cancel out A, this is the ratio of angular dispersion upon mean deviation. Angular dispersion upon mean deviation is called dispersive power. This is known as dispersive power. So dispersive power is ratio of angular dispersion to the mean deviation. And dispersive power of a prism that is depending upon the material of the prism. This is with respect to any two color. It is defined as ratio of angular dispersion for two colors to the mean deviation for that means prism. Mean deviation produced by the prism. Mean deviation produced by the prism is mu minus 1 into A. So this was angular dispersion for two colors, and this was mean deviation produced by the prism. And we write down it as a, we can write down it as a d mu upon mu minus 1 is equal to omega. So this is the value of this. purpose. So this d mu is mu v minus mu r. We will take this case, and if we do the inverse of this dispersive power for two colors, the value becomes, depend upon the nature of the material of the prism, that becomes the constringence. If I take the inverse, it becomes constringence. This is called constringence. So this was the angular dispersion and dispersive power. Now I will talk about in the next lecture. In the next lecture, I will talk about the deviation without dispersion. Deviation without dispersion, I will talk in the next lecture.